So this is a very experimental talk. We heard very nice things about how the theorists have been banging their heads against theories for the last 30 years. Well, experimentalists have been doing the same, actually trying to kill off many, many theories over the last 30 years. And that I'm pretty much a child of the Standard Model. So I started in 1982 looking at particle physics, and the Standard Model was king. And I've pretty much spent the last 30 some odd years trying to see where we can find the direction to go. In fact, the Standard Model has given us a lot of beautiful hints along the way about things we had to uncover as experimentalists to wipe out lots of theories. And I wanted to spend a few minutes talking about that journey and then talk about where we can go from here. So when I started, it was just about the time that W and Z had been discovered as real bosons, and it just seemed easy. New physics would probably be just around the corner. I think I started hearing about supersymmetry at the first summer school I went to in 1983, and it's been just around the corner ever since. But there was just a few loose ends to tie up, and this is my first precision electroweak measurement of the Standard Model. And in fact, the Standard Model gave us a really good, big separation between the number of light neutrino generations. So this was 2, 3, and 4. So even with a small number of E plus E minus going to Z, you could make a big prediction from the Standard Model. This was the easy one, the lowest hanging fruit. And of course, there was a number of other outstanding parameters, the top quark, a detailed mass of the bosons. But we were able really very, very quickly to work out that there were 3 light neutrino generations. And in fact, when LEP turned on, this became a really started the era of high precision. Now, the next test, and this is a beautiful part as an experimentalist for the Standard Model, is it also guided us as to the biggest term we needed to settle, which was the directions from the top. The top was probably the heaviest thing. And so we as experimentalists looked and we said, even with this small data set I showed you before, there was a pretty big dependence on the top mass of any observable we wanted to do. And at LEP, we measured an infinite number of observables. And very, very quickly, between 1990 and 1995, we had understood the Standard Model was telling us this is exactly where the top has to be in order to be consistent with all the measurements you've made. So I'd like to show this example to students of how, well, this is a really good theory. If you follow it and measure everything it predicts, the consistency of it tells you a lot about the things you don't know. So we of course, it all worked out beautifully, and we continued this game looking for the Higgs. And that, this was where all these data, and there's only a logarithmic dependence here. So there's a quadratic dependence with the top mass. So that, that was a very easy thing to see. It was very easy to find that. The Higgs, you really didn't get superb limits, but in fact, it's very, very close to what turned out to be the answer. So this is where we are now. And as an experimentalist, this is a beautiful plot and a really frightening plot, because this is 7 orders of magnitude of predictions that lie just spot on where the Standard Model is. We've pretty much understood the parameters with great accuracy. Now what? How are we going to push that? So we know when we run the LHC some more, we can go to other modes, even rarer, that the Standard Model predicts and look for that. But it's just too good. It's really challenging, not just for theorists, but for experimentalists as well. So what do we need to do? What's an experimentalist going to do to give you some challenges as theorists to figure out what the next direction might be? So what's a good place for an experimentalist? Well, obviously a reaction where you can make a very clean measurement is very important. And the calculations, okay, if there's not too many weird hadronic corrections that you can hide behind, but very clean corrections, very clean theoretical prediction, that's great. You want something where the Standard Model contribution would be very, very small, but a new physics contribution would potentially be very, very, very large. So where we've been looking in the experiment which I'm going to talk about, the COMET experiment, is a diagram like this, where you get muon to electron conversion. Now this is a Standard Model process. Now that we know that neutrinos mix, that's there. And you just write it down and you calculate the branching ratio, and it's only 10 to the minus 54. So even as an experimentalist, I realize it's a difficult challenge to do, right? I make muons by bombarding a target with protons. If I took all the protons in a gas giant planet and bombarded them on on a target, I could get a number about like that. So it's going to be really hard for me to get funding to do a measurement at 10 to the minus 54. And we should be able to, if we see anything here at anything level we can measure, it's not coming from the standard model contribution. So this looks like a really good place to look. And the experimental signature is quite simple. You've got a photon and an electron coming out. In fact, you can do a couple of other different types of ways of looking at this. You can look at one where you recoil off a nucleus, so you get direct mu to E conversion, or you can do mu to E gamma. These are sort of leptonic couplings, or fermionic couplings, depending on which extension of the standard model you want. This is a very generic way of writing down the types of ways in which you can see these. Experimentally, you see either mu to E gamma, or you see muon to electron conversion. Muon to electron conversion around a nucleus could have contributions from the 4 fermion type coupling or the leptonic coupling. And if you want to look at where the best limits are at the moment, in terms of muon to electron conversion, it's sitting here, and mu to E gamma, it's sitting here. This is the parameter which tells you how much photonic coupling and how much 4 Fermi coupling, and you can see that mu to E gamma experiments at the moment are the most sensitive. Muon to electron conversion experiments are more sensitive if it's a 4 Fermi coupling. And there turns out that experimentally, mu to E gamma experiments just run into real difficulties with accidental rates. And so to push these sort of searches and to be more general across any type of interaction, muon to electron conversions give you a real possibility to do this. So I just picked a few channels. I mean, I'm sure that your favorite theory has probably been calculated this contribution, because it's something that actually has a pretty stringent limit on standard model processes at the moment. And in fact, simple supersymmetry is really already hard to accommodate with the measurements that are there. You get a big term because of the mixing in the lepton sector. It depends what you consider as the right reason for that. Z primes can give you 4 fermion type contributions, and you can go and read lots and lots of predictions about levels at which you would see contributions from supersymmetry into muon to electron conversion. So now is where we are now. These green points are assuming that leptons mix like neutrinos with a big mixing. This is assuming that the leptons mix like CKM, and these are future experiments. So potentially these sort of experiments will explore a very large part of supersymmetric models. Here's another limits on Z prime productions. So you can go through and make a large number of calculations and see how well does this experimental challenge do at closing off different theoretical models. So this is a job best left to theorists to go through and grind through their favorite theories and see which will give a decent signal in which channel. So these are different experimental channels, and these are the two I'm talking about. And you should believe in this, that 3 red stars is a good possibility to see something. And so these channels actually across the board in a large number of models really do give a good possibility to see something. So as an experimentalist, you think, okay, that's a good place to look. Now, how am I going to do this experiment? So these experiments have actually been going on a long time. I mean, Pontecorvo did the first one in the 1940s, and essentially they've been getting better by about 2 orders of magnitude a decade, is where we're sitting now. And the limits are now around 10 to the minus 13 or so are the current best limits on these. And so what we're having to look at is how could we push this for the next generation to actually get limits that are even substantially better, 2, 3, or 4 orders of magnitude better than what's available experimentally now. So what's the practicality of making one of these experiments? Well, the basic idea is you just need a lot of muons, like 10 to the 20th muons. They need to be really slow. You take a big beam pipe and you make your beam of muons as big as you can. You have a bunch of thin targets sitting in the path of these muons, which they have 40 MeV of momentum, 30 MeV momentum. So when they hit a thin piece of target, they stop. They make a muonic atom, and you can get 3 different ways in this might decay. So the muon can decay as it's orbiting in the muonic atom. You can have a straight nuclear muon capture, or you could have this conversion reaction where the signal you get out this is neutrino-less muon to electron conversion. The signal you get out is 105 MeV electron coming out. So it's a monoenergetic electron. It's a very clean signal in principle, and the ones that come out here, the decay in orbit ones, have a much, much lower energy for this electron, and then nothing here. So in principle, the signal's nice. This is the electrons, so the muons which decay as they're just orbiting, so they don't capture, they just simply decay. They have a spectrum like this depending on the target material, and you see it cuts off nicely at half the muon mass, so it ought to be able to really separate from the electron signal, which we're trying to look at over here. But if you look in detail about what's going on in the tails of this distribution, you do get contributions at 10 to the minus 16, 10 to the minus 17, 10 to the minus 18 when you get out to the edge of the spectrum. So this ultimately can be a limit for us experimentally, even though you're very, very far from the peak here. That tail is something that we have to look at rather importantly. So this is the current state-of-the-art experiment in muon to electron conversion. It's called Syndrome 2, and it was running at the PSI beamline. And you can see here, this is that tail of decay in orbit electrons coming from muons which decays in orbit. A signal of a conversion would be here. It's a little less than 105 MeV because of their experimental setup. The electrons would lose energy in their setup on the way to the detectors, but that's where they would expect to see a signal. And one of the problems they have is that the muons that they make are very close to their muons are made by basically you take protons, you bang them on a target, out come lots of pions, they decay to muons, but there's significant contamination in this beam from pions, and so they have to you can see here is a little attempt to look at events that look more like pions, and these are events where by using timing information you look at events that look more like muons, but this is where their contamination limits are really coming from. This beam has a real limit in terms of pion contamination. And it has currently set a limit of about 10 to the 7, 10 to the minus 13. So what are the elements of making an improved experiment to do this? So the first thing you need is more muons. So the PSI beam was making about 10 to the 7th to 10 to the 8th muons per second, and the aim is to use a dedicated beamline at the JPARC in Tokai in Japan, the JPARC Hadron facility. It's a 56 kilowatt line, and the aim is to get about 10 to the 11th muons per second, and this is the dedicated line, and here is the experimental hall which will hold COMET, and these scales are small. These are, these experiments are much tinier than the ones we've been talking about that are measuring at the LHC, but they still have their complications. So let's go through a little bit about how you do this practically. So the first thing you need to do is make this very intense beam of muons, and then you start with an 8 JeV beam of protons, about 10 to the 12th protons a second. You put a target inside a big solenoid, and the beam goes from here to here. Here's the target, and most of the beam then ends up in a beam dump, but pions you make come out in all directions, and you want to capture with the magnetic field of the solenoid the backwards going pions, which will be the lower momentum ones. And in fact, you shape the field a little bit so that you get the pions that are coming out to more or less come out in a great big, it's a quite wide beam, about this size, and the bore of this at the end should be full of low energy muons coming out. So there you go, you've now got a source of low energy muons. And now you want to do something to get rid of the pion background. So one thing you could do is actually don't run your beam all the time, you run it in pulses. So you have the beam come in 100 nanosecond pulses. There'll be a tremendous background from things like pions and beam particles, but you're looking for muon captures. And in fact, the lifetime of muons which have stopped on an aluminium target is at nearly 900 nanoseconds. So they have a long lifetime, and if you put a microsecond between the beam pulses, you can ignore the beam flash from this big splash coming out of your proton source, and then you have only the muon decays and the muon captures, which are happening out here in a very clean environment compared to the beam. So this is an improvement over the previous experiment where it was constantly being contaminated with the pions. You use this beam there's the shape of the beam and the timing of the beam to help you get a very clean environment. Now, of course, it's really critically important that there's no beam that sneaks into in between these two flashes of the beam. Otherwise, you have a potential source of background coming in. And in fact, you create these pulse beams by you have accelerators where you don't fill every single bunch. And then you can do this and measure what's called the extinction. It's how many protons you get in between the bunches. So in between this window, how many protons you can get. And in fact, we need to get something around 10 to the minus 9. And that we've been able to achieve by changing the RF frequency at which we extract the protons. And so that's now proven that we actually can get a quiet enough period in between the beam pulses to look for these muon captures. So here's the basic experiment. The scale here is, this is about 5 meters. And here's the target I showed you where the protons come in. They're captured here. Backwards going out of that are pions. And they decay as they're moving along this. So this is a curved solenoidal field, which transports and allows you to do some momentum selection, charge selection, and it allows the pions to decay. Then here's the stopping target. These are the little places where you've got a very big beam pipe here full of muons, which you've now selected to be low energy, quite clean. The beam is over here, and this curvature means that you're a little bit protected from lots and lots of backsplash from things that happen here. So here's your target where you're going to capture the muons, and then over here is your detector. So you have yet another transport section which is optimized to transport the electron signal electrons, but not the decay and orbit electrons, which have half the momentum. So you want the 100 MeV electrons to come around here and the 50 MeV electrons to stop, so that the rate in your actual detector here is quite quiet. You have a good number of muons which stop on the stopping target to give you lots and lots of possibilities to do this, and you have a good clean signal when you get around to your detector. So this is the collaboration. Again, it's relatively small compared to the modern collaborations. It's 179 people, and this is the actual experimental hall, so it's something that's really being built. This is the first thing I want to talk about is this bit here, this muon-transport. So the pions are decaying in here, and you want to reduce muons that decay to electrons in this section by doing as much charge and momentum selection as you can here, and you do this with collimators and with setting the magnetic field. And if you look at this, by the time you get to the end of this, you get a nice set. In green is the muons you want, and red are things you don't want. So you get a nice set of the particles you want, the muons in the stopping target. This is the actual transport solenoid, so it's again been built. It's being installed now, and this is the next section of this is the detector section. So we now have in the stopping target a nice clean set of muons. We now have to have something to look at the decays that come out, measure the particles that come through, and we're going to use this spectrometer to select the electrons that come through. And here you just see a cartoon of a collimator. These are the targets. They're aluminum discs. If we make an electron of 105 MeV, it will spiral through this curved solenoid, go through our tracking detector and calorimeter. We'll get a nice clean signal, and we block electrons that have lower energy. So we should, in principle, get a nice clean signal at the end of this. And here's some pictures of just simulations of what the muon flux looks like at the stopping target. There's 17 200 micron thin disks, and we keep them thin because we don't want to ruin the electron resolution as the electrons come out. And you can see that the different pieces of the transport section serve to get muons here, but not let them come down here, and to keep the pions from getting into the detector section. This is just a picture of what events look like in here. There's 4 simple layers of straw trackers. They're relatively simple devices. They're made by using straws, which essentially there's 20 layers of straws. They're not hugely big. This is the size. You can see people here, and this is a prototype that was built last year and put in a beamline, so you can see that these straws are ready to be assembled. They need to be quite thin because experimentally you want to get very, very good electron resolution. The resolution of the electron is going to absolutely limit how well you can do on this. And so you make these straws very, very thin, a 20 micron thick wall, and we've shown that we can actually get very, very good performance in order to get the type of resolution we need to get a good measurement. The calorimeter is a crystal calorimeter, which is sitting behind the tracker, and the electron should go in there. We want less than 5% resolution at 105 MeV, and very quick response time of about 100 nanoseconds, and it's going to have to operate in a vacuum and a magnetic field. And we've chosen in the end to use LYSO crystals. You see one of these crystals here, and here is just a picture of a beam test which was done comparing the two different types of crystals. And you see that the resolution that we're getting out of this crystal calorimeter is about the 5% we needed. So we will use the LYSO, and it will meet our energy resolution of 5%. So here's how we actually get the number out from the expected performance from the experiment. This is what you actually want to do, is figure out how well is this experiment going to go. And the idea is to actually get 4 orders of magnitude improvement. So to get down to 10 to the minus 17 level. So what do you have to do that? You need to put 10 to the 20th protons on target. You need to have a number of stopped muon is around 10 to the 18th, and that's going to allow you to get something down to about 10 to the minus 17. You capture about 60% of them, and you have this much acceptance in your detector. And if we get this performance out of the COMET experiment, we will get a confidence limits of about 10 to the minus 17. So one of the things you learn experimentally is that trying to improve something by 4 orders of magnitude is actually kind of a hard call to do. You don't like to make an experiment that's immediately going to do 4 orders of magnitude improvement, because on a very, very sensitive experiment like this, it's likely you'll run into things you didn't think about, and you want a chance to be able to understand what those are and maybe make some improvements to your experiment. So what we're hoping to do in COMET is actually do something called Phase 1, which is where we take the detector here, we take the transport solenoid, which I saw you a picture of there, and essentially we just mount the detector here and use this to study the beam and actually to make an early first measurement of mu to E conversion. So we put a target here, we put a detector around the beam line there, and this allows us to actually measure the properties of the beam very accurately, and we hope also to make at least a couple of orders of magnitude improvement in the measurement of mu to E conversion. So the target of this phase, which is Phase 1, is to make a measurement of around 3 times 10 to the 15, which is roughly 2 orders of magnitude better than where we are now. And it's, again, as I said, it's very simple. You have the same elements of producing this muon beam, and then it transports through the first 90 degrees, which should give you a reasonably pure muon beam. And then you're going to put a detector here to look at, put some targets here and put a detector here to look at what comes out. So it turns out, if you put the detector we're planning for the end of the beam here, that has the beam going straight through it, there's way too much beam there. So this is the wrong place. There's way too many particles. So we couldn't actually run the final detector even at the intensity we're hoping there. We'll have to run at a lower intensity to understand the beams, but we can put a different detector around the beam line. So you essentially let the beam go through, the targets are here, and you put a cylindrical drift chamber around, and then 105 MeV electrons, which are made in here, will spiral out and go into this drift chamber, and you can actually make a measurement of the muon electron conversion. So this is, for instance, what a signal would look like. Anything less than 60 MeV will just spiral around in this chamber. So it does a good job of selecting away the decay in orbits, but you will get 105 MeV electrons will make it out to the outside, and you will get a decent signal to allow you to make, hopefully, a preliminary measurement. So this chamber is actually currently under construction. Again, it's not a huge thing, but you see it being built here, and the wires being put on. And in fact, the wire stringing of this chamber was completed in November, and for about 122 days of work for 20,000 wires. And currently, the last few bits of it are being put together, and it will be turned, gas will be put on, and it will be tested during the spring. So what's going to limit this experiment? Well, where we've put the detector, so if you remember the option here, the detector is sitting here, so the decay in orbit is going to be much greater. We don't have this section of the solenoid which is going to select out and help us block decay in orbit. So we will be limited at 2 orders of magnitude higher by decay in orbit. So the ability of this, us to measure the resolution of this signal is going to tell us how well we're going to be able to get a signal out, and we're aiming to get 3 times 10 to the minus 15, where this would be the tail of the decay in orbit in that detector, and this would be a signal. Again, you can look at what we're hoping to get. We hope to get around 3 times 10 to the minus 15 single event sensitivity, which is 7 times 10 to the minus 15 confidence level. We would need about 1 times 10 to the 16 muon stops, which is going to take about 2 times 10 to the 19 protons. And we can do this in a few months of running with a low power beam. So it runs at relatively lower power. And the main background that we run into is this decay in orbit background, which I showed you here, where you have this long tail of the electrons which decay orbiting around the muon, the muons which decay orbiting around the nucleus, interfering with the signal. When is this going to happen? So the current planning is the construction's been going on the last few years, data taking hopefully in the Japanese fiscal year 19 for phase 1, which will get 3 times 10 to the minus 15 in 110 days, and then phase 2 sometime around 2021, which would try to get to 10 to the minus 17, so a 4 order of magnitude improvement with the higher power beam. So I could summarize now and just say that it's actually quite a difficult beast experimentally to attack the Standard Model. We just know it too well, and it's going to be hard slogging if there's no new physics showing up right around the corner at the LHC in the next year or two. We're going to have to look at all manner of attacking. So from general purpose detectors at the energy frontier to these are high intensity detectors looking for hints of something in a very, very unusual channel that could allow us to see some difference to what the Standard Model is now incredibly well constrained. This channel is one that offers a real potential window where new physics could show itself. There's 2 experiments being built. One I didn't talk about called MUT-E happening in Fermilab and COMET, which are going to run at a similar timescale. And I think these experiments offer the possibility of making a substantial measurement with a hope to see something if one of these many theories which are on the market predicting something will be there actually has some connection to nature. If it's just the Standard Model, we'll never measure anything here, and that's the way it's going to go. I hope we measure something. I don't want to go my entire career only measuring the Standard Model, but it'd be nice to know the next step. And so this is one of the ways in which we hope experimentally to be going after that. So that's it.
Well, I'm very glad that this experiment is going in. This was the sort of project which was thought about even before the construction of JPARC itself. I have a couple of questions. I understand you are using a mu minus, right? Yep. There is some problem. I know there is some problem with mu plus. But my first question, is there any sort of thought about using mu plus? Another question is, what's the reason you chose this aluminum as a target? The CDC has a 5% energy resolution. Is there any way to improve that? Because, well, you probably will see, first of all, the orbit, decay in the orbit first. And it's really at the very tip of and energy resolution is crucial in this distinction. So these are the three questions.
So the target is aluminium is good because the lifetime is long. So you can use titanium, but the capture lifetime is shorter. But one of the things that's nice about these experiments is that if you vary the target material, you get a different non-standard model contribution. So if we do see something, we can change the target material, and we should see different rates for new physics. So we are thinking about different target materials, but aluminium has a nice lifetime and relatively low interference. The energy resolution, you're absolutely right. We're completely dominated by that tail of the decay in orbit. And I think it's in the phase 1 where we have a CDC, that's the case. In phase 2, it's not really the case because we have the transport solenoid for the electrons, which will help reduce that background a lot. But there's not so much we can do other than making the resolution the best we can on the drifter, because we're going to have so many decay in orbit muons. We're not selecting them out, they're happening right in the middle of the CDC. Mu plus we're not capturing. So you can do some experiments looking decay in flight and things, but no.
Okay, well, if there are no further questions, let's thank Jordan again.